Good morning everybody and welcome back to this program again, lectures on distribution theory and Sobolev spaces. So, in the last class we have introduced the distributions after giving enough motivation, and we also see that the class of distributions is nothing but the dual of the test function space d omega, which is extensively studied in our preliminaries, and we are given lot of functions. We have seen that all the locally integrable functions and more generally all LP functions are defines a distribution. So, we also said that we will not distinguish function and its distribution. F is a function, LP function, TF is the distribution. So, quite often we write it as F. We will initially say that again and again. And after that function, we have also seen that Dirac delta. Dirac delta can be viewed as a distribution which Dirac envisaged, but we also mentioned that Dirac delta can be viewed as a measure. With respect to measure, you can actually get what Dirac wanted, but not with the derivatives. So, in fact, the Dirac delta is not the only measure which defines a distribution. So, what we are going to see, and another example, every measure example any Radon measure defines a distribution. Any Radon measure defines a distribution. Defines a distribution. How do we define? What is the meaning of Radon measure? So, mu is the Radon measure, that is mu of k is finite, it is a measure for all compact sets. Okay. So, define T mu from d omega to r by T mu of phi is equal to integral d phi dv, okay, over omega. And I said as soon as you define a distribution, you should verify the well definedness. The well definedness is fine because basically phi has compact support, and hence the integration is over a compact support compact set, and since mu is a Radon measure, this is finite. There is no even modulus is finite. So, that is not an issue. You can also check that it is linear, obvious, and you can also check it is continuity because phi n converges to phi or phi n converges to 0 in d omega. So, it is a uniform convergence, and then you can pass to the limit in integral of phi dv. That is you can actually see that if phi n, these are all trivial to check, but you should check it. Phi in d omega implies d mu of phi n because it is a convergence of the integrals under uniform just to d phi. Okay. So, that part is thing. Here I want to make one remark. So, this is a class of examples. In fact, I just want to say something more about it. So, you recall the basics we introduced in CC of omega. This is set of all continuous functions with the compact support, and by you know that this is the d omega function is continuously embedded here, because d omega is a CC infinity of omega with that inductive limit topology. So, in the preliminaries we also introduced the topology is a similar way, you can introduce topology not only on CC of omega, we will make more comments later, but you can also introduce a similar topology to make it a topological vector space, and with respect to, so d omega and CC of omega, so d omega is contained in CC of omega and the identity mapping is continuous under that topology. So, d omega is embedded in CC prime of omega. So, with that you can this is you can see that the d prime of omega contains CC prime of omega, you see. So, in other words, what it shows that if you have, so this is precisely the class of measures, this is what class of measures, that is what you would have seen it already, the set of all probably you would have seen it C of x, where x is a compact set, then C of x can be, its dual can be identified by the class of measures. So, that is what essentially we prove these are random measures, you can put it in d omega and you see that one. So, as a distribution, so this recognition C of omega as a class of measures you know, but as a distribution this is a special class of distributions, that is what you have seen it, special class of distributions. So, special class of distributions. You will see soon not only CC prime of omega, you can talk about CC1, that is once differentiable CC2, CC3 etc. In fact, these are all introduced, CCK, up to k times differentiability, and you can see CCK of its dual. So, these are all we will discuss it a little later about that one. So, this is just I want to, so in other words this also continues, so you can talk about it, you can give the topology and then the CC prime of omega will be contained in CC of omega. So, let me now go to the next stage. So far you have seen only distributions defined by functions and measures, where we have used to check the continuity, you have only used the uniform convergence of phi n. You have never used the because if phi n converges to phi, in d omega all its derivatives are also converges uniformly. But so far to check you have seen only the familiar objects of distributions, because the measures you know as distributions and the functions LP functions are distribution. Now, I am going to give you a something new example where you cannot view a new distribution which cannot be viewed as even as a measure. Okay. So, you are going to define phi going to minus 1 power k phi prime of 0. Of course, to define this one, this is of course to do minus 1 power k does not have much significance right now, but later you will see k times pi per k. Okay. Right now minus 1 power k does not have much significance, but you will soon see these are all derivatives of the Dirac delta. Okay. So, you can trivially varies, trivial to c. So, let me, what is the mean t going to phi going to trivial to c, this is not very difficult, trivial to c t is in d prime of omega. Okay. So, you see it defines all the distributions. So, you have a family. To verify this one, you need the convergence in d omega up to k derivatives. So, it is just uniform convergence in d of the function is not enough, you also need the convergence of the derivative. So, if you so you can I will leave it as an exercise now. For example, phi going to first thing minus phi prime of cannot be represented by a measure. Forget about the function, cannot be represented by a measure even. What is the meaning of that does not exist, that is that does not exist mu a measure such that minus phi prime of 0, this is what you want. You want to represent it as phi d mu. This is not possible. So, that is an exercise. Just like phi 0 cannot be expressed as integral of f dx. You cannot given by a function. In this case, you cannot even given by, but you have seen that delta is a measure, but this is not even a measure. You can do that one. So, in this thing, so let me make now some remark. So, you recall modifiers. Rho epsilon, and you seen that the rho epsilon converges to 0 for all x not equal to 0, and that is why we, of course this is a question, is it close to delta? Yes, if you want that one, the initial motivation is that delta x equal to 0 except at one point. Now view it as a distribution, view T rho epsilon. What is T rho epsilon of phi? Integral of rho epsilon of x, phi of x dx, right, in R. And this is already given as an exercise, or if it is not done, you do it at this stage. This converges to phi 0, which is your delta phi. You see, if you are not done, do this as an exercise. Yeah, little bit of work you have to do, because rho epsilon is as it becomes sharper and sharper, it concentrates, and so you have to carefully deal with that one. So, this is precisely, that is, you see, T rho epsilon, exactly what we want it. So, if you view it as a function, if you view it as a distribution, this converges to delta in D prime. This is nothing but your weak star convergence. So, you see, so you have your convergence in D prime of R, and this is what exactly we were looking at it. On distribution, you have your Dirac delta. So, one more comment I want to make here. Yeah, so the comment I want to make here, from now onwards, we will not distinguish, So, when whatever, even if I write some other distinguish f and Tf. So, what does that means? That if Fn converges to f in D prime, means Tfn converges to Tf in D prime. That is the meaning of it. So, in this sense, we also write rho epsilon converges to delta in D prime. You see. So, we will not all the time say that, of course, this is as epsilon goes to 0. A minute. All right. Now, we will go to the next concept of distribution, mainly the derivative of distribution. we already motivated the derivative. Suppose f is locally integrable, that is we say f is a locally integrable function, and then we then we have seen that a weak derivative, we already defined a weak derivative of a locally integrable function, T f of phi is equal to minus f phi prime. So, basically you take the derivatives on phi prime each time you have adding a multiplying by a minus sign, and this is we have obtained by using the integration by parts. So, with that let me give you the definition. You can define the derivative. So, the T is very general object now, including all functions, measures and more functions, more distributions we have seen. So, the new calculus, it tells you that you can define the derivative of any distribution and as many times as you want, which that facility was not available for functions. So, the class of functions which are differentiable is smaller than the even continuous functions. So, let T belongs to d prime of omega, define d power for any multi-index alpha. Alpha is a multi-index. So, we will define d prime of alpha from d omega to r by d power alpha of t acting on phi is equal to minus 1 power mod alpha t acting at d power alpha of phi. You see, for all for any, this is true for this is we are defining for all phi in d omega. This is for any multi-index alpha equal to alpha 1 etc. alpha n, where alpha 1 etc. alpha n are non-negative integers and mod alpha is equal to alpha 1 to alpha n. So, you see you can define that, easy to check. So, it is easy. So, you define check d power alpha of t is in d prime. That means d power alpha of t is linear, that is trivial because t is linear, and the continuity is also easy to check because if n converges to 0 in d omega, all its derivatives converges. In particular, d power alpha of n converges to 0 uniformly. Since t is continuous, t of d power alpha of n converges to 0. That means d power alpha of t acting on phi n converges to 0. So, you will get immediately this one. This is easy to check that one. So, let me give you a couple of examples maybe in the next slide. Now, you know the examples. So, simple examples we can see. Example. So, consider this function f of x. This we have more or less done probably earlier, mod x, say in minus 1 to 1. So, this function is this one, this is your mod x, this is your mod x, okay, 1, 1. So, we want to know that 1. Of course, f prime equal to 0, f prime x is for all x, x is for all x not equal to 0. In fact, f prime of x equal to minus 1, this is classical. So, we want to know what is, whether classical derivative is the same as, does it give the distributional derivative will give something new for minus 1 less than or equal to x less than 0 plus 1 for 0. At 0 it is not defined. So, let us compute your df acting now distributional derivative df acting at phi, that is equal to minus so what is that one? So, Tf acting at phi is equal to nothing but the df means so okay, so this is the notation dtf if you want. So, I said I won't distinguish much. So, df means the corresponding derivatives of first time on right. I will not do this all the time. So, Tf means we represent by f when it is viewed as a distribution. So, this is nothing but minus 1 to 1 f phi prime. So, that is become minus, now f is mod x. So, it will be minus 1 to 0, it is minus x phi prime of x dx, because I cannot do an integration by parts here. So, integration by parts cannot do it because f is not differentiable. So, I split this integral into 2. These are the small tricks you may have to do it again and again. 0 to 1, here you have x phi prime of x dx. Okay. So, that is equal to, so you now you can do a minus 1 and 1 will get cancelled, you can do an integration by parts. When you do an integration by parts, it will bring one more sign. So, you will get minus 1 to, so there are already 2 minus signs, one more sign will come and the derivative x will become 1 minus 1. So, there is one more minus sign and you will get phi of x dx, and then you will have this boundary terms x minus 1 to 0. Here the same thing, but you will have a plus sign, integral of 0 to 1 phi of x dx, and then you will have minus, that minus will bring x phi at evaluated at 0 to 1. Now, look at here, phi 0 not necessarily 0, but phi at minus 1 is equal to 0. So, phi at minus 1, because it has a convex support, phi at 1 is equal to 0. But at 0 x will make it 0. So, this term will get cancelled. Similarly, phi at 1 is 0, but x is 0 here. So, this will get. So, I can immediately write down this is equal to 0 to minus 1 to 1. I will write at g, I will define what is gx, I can write gx phi x, where g of x equal to minus 1 for minus 1 less than equal to x less than 0. So, plus 1. So, 0 less than x less than equal to 1. So, you see. So, that means that is a way whether my distributional derivative can be identified with a function. So, that implies my df, the distributional derivative is same as g, that same as f prime. So, you do not have anything new. So, it is identified your though initially started with your df, not necessarily you may not be able to represent it. So, that is example. Next example I want to do it. So, I think you can work it out more. So, I will only write it here example. So, you do the simple computation. So, I want to define the famous Heaviside function. This is your Heaviside function which I already defined, 0 minus infinity less than x less than 0. This is 1 0 less than or equal to x less than infinity. This you already seen it. This one, right? This is your h. Then you have your classical derivative x again, the h prime of x equal to 0 almost everywhere. In fact, this is equal to 0 for all x not equal to 0. So, except at x equal to 0, you have your let us see whether we can get it. So, you can immediately now compute. So, compute is a small computation, compute the distributional derivative evaluated at phi, that means dh. Again I am repeating, I am writing the same thing, that is equal to minus 0 to infinity phi prime of x dx. This is much more easier than the thing here, but then now this is 1 here. So, if you do an integration by parts, nothing will come, but only the boundary terms will come. So, the boundary term is minus phi at 0 to infinity, but you know that phi at minus infinity phi has compact support, and phi at infinity. I should not be writing this way, but basically see that phi identically 0 outside a compact set, outside any finite interval, outside a outside a say minus m2 m if you want to call it, outside a finite, because of the compact means it will have non-zero values inside a compact interval. So, the phi at infinity is 0. So, this is nothing but phi 0. That means this is nothing but your delta phi. So, this implies your dh is delta, which cannot be, we already seen that. So, even though h prime, so there is a singularity so there is a discontinuity happening. At that discontinuity that it contrary the distributional derivative and this is precisely, there are historical thing, and this is precisely the idea of Dirac and engineer. How do you look at it? This kind of discontinuity produces your Dirac delta. Okay. So, the signals venue. So, these are all introduced by engineers, Heaviside function for their analysis. Okay. So, in fact, you can do more about it. So, in fact, you can keep on computing this one. In fact, you can compute the k plus 1 derivative of the Dirac delta, and you can see that this is phi, this is nothing but minus of, not minus, minus I will put it later, this is equal to d power, because the first derivative. So, this is nothing but dk of delta phi, and this you can do it as a small exercise. You can see that this is nothing but minus 1 power k, and delta is a distribution. So, you can, so you see now you because after the introduction of the derivative you have delta is in distribution d prime of r. So, delta prime, delta double prime as distributions you can define, and these are all distributions. Okay. And that distribution is given by this one. You can prove this actually if you want that one, phi power k evaluated at 0. You see. So, if you are not convinced, prove it as a small exercise. Okay. And this we call it, this is precisely your the kth derivative of your phi as distributions. So, you can differentiate now, and this is precisely Dirac was whatever you wanted it when you evaluate. So, you do this one. Okay. So, I want to give you little more general exercise. You have a like it is a more general cases. What we noticed, when you have continuity, you are not picking up anything, but when you have a discontinuity, it picks up something. So, this is your exercise, you can do it. So, more generally, suppose f is in piecewise differentiable, piecewise differentiable. So, as a simple case, f is differentiable except at one point, f is differentiable except in AB. So, I will write it in AB. So, f is differentiable except at C belongs to AB. This is what I am at one point. So, I am looking, A is here, B is here, so C is here. So, I have a nice function here, and it may be continuous, it may not be discontinuous. So, f is differentiable except at point, and f prime is locally integrable in AB. So, f prime also defines a distribution. Okay. So, in that case I want to know then what I am trying to prove to you, then I want to compute my df. Okay. That means f prime classically existing, because f prime is differentiable in both A to C and C to B. So, you can define f prime classically in A to C and C to B, but not at C. This is exactly like your Heaviside function. So, then the df, the computation of your df, that is same as your dtf, sometimes I am writing, is same as the distribution, because f prime is locally integrable. So, f prime defines you a classical, it defines a distribution. So, I know that is a distribution given by f prime, and then you will have the jump of f at C, jump of f at C into the Dirac delta C. You see. So, what is jf at C? So, it is so the f of C plus minus f of C. So, you are basically assuming that the left and right continuity, the left and right limits of f axis. So, you see you can compute. So, in fact, you can generalize this result to more that one. So, if you have a function in AB, so write down the problem and solve it. So, the next exercise, generalize it, generalize and prove. So, your problem, you should also know how to write exercises and prove. So, if you have some set of discontinuous points C1, C2 etc., some Cm, and you have a smooth function here like that. So, it will pick up, and you assume, so you have functions which is differentiable. So, you can differentiate except at finitely many points, and each time it will pick up a Dirac delta together with its jump. So, you can write down your distributional derivative in terms of the classical derivative. So, the distributional derivative will have a classical part if that classical part defines a distribution together with the distributions which are not functions. All right. Okay. So, probably let me see. Okay. With the last one, and I will confuse one more thing. I want to give it as an exercise, then I will continue after a few minutes. Look at log mod x is locally integrable in R, locally integrable in R, right. The only singularity coming at 0, and that part you know log mod x is locally integrable, and otherwise it is a continuous function, so at infinity. So, anyway, so you will be dealing with. So, as a function, what is dtf? That means what is df? as a distributional derivative. What is this? So, the exercise that prove that this is nothing but your principal value of 1 by x. Okay. So, that is a very nice exercise to be proved. So, that time I remember. So, this is one way of proving. I told you proving distributional derivative. Now, proving that PV of 1 by x is a distribution involves little work, but we can prove that df equal to PV of 1 by x log mod x, because it is locally integrable, is indeed defines a distribution, and every derivative is a distribution. So, that way PV of 1 by x as a corollary proves that it is a distribution. In fact, this is the idea, you have to use it to prove PV that limit exists and all that. Okay. So, I will stop here and continue in my next lecture some more ideas. Okay. Thank you.